Hello, everybody. We are live, episode 2 of Zero to Zero Day. Thanks again. I hope y'all can hear me. If not, oh well. I've gotten some requests to record these and upload them. I am recording them locally, and then I'll upload them. I've also heard there's some buffering on Twitch. I don't know. I can always reduce the resolution. If I reduce it too much, though, it's probably gonna be hard to read. But y'all let me know. It's the first time doing this, so I'm not sure exactly what the right settings are. But I want y'all to be able to watch it and enjoy it. So just feedback's appreciated. Also, thanks to everybody for some of the shout outs on Twitter. It's just really encouraging. So appreciate it. Let's jump in. One more thing. If I did get one comment on the mic. If this mic doesn't sound better, I turned it down a little bit. I'll get a different mic. So we're just gonna give it one more shot and then figure something else out. So where we left last time, we kicked off the GPU. We talked about kind of what we wanted to find in this thing. And first thing we did was kind of walk through how the drivers are loaded and how you can find out what drivers are loaded. And one second, good feedback on our Discord channel over here. By the way, join the Discord channel. I'm putting links into there. I'm putting links that you can look at throughout the week until the next episode, and I look at before the next episode. I really am not. I wish I could. Normally, when I'd go into a project, I'd start and I'd do 8 hours a day. I'd spend 10, 12 hours a day. I'd really get in the zone. Sometimes that's what it takes. But for this, I'm just kind of doing it, 1 hour a week as my time allows. And hopefully, we learn something. We may not be successful, but we're going to learn something. So, okay. So we looked at the driver. We found a few interesting things. We did see that there was a device that was opened called NVAdmin device, and I noted before that looks, something that you may want to investigate. My understanding is that it's likely one of the devices that you open and you send IOCTLs to, which is IOCTL is just an IO control or IO request packet, and it's a way that software can talk to the driver. And there's an abstraction between userland and the kernel. And there's been a lot of bugs there, and I'll show y'all after I went searching. You're always going to find researchers that have either looked at something before you or have dabbled close. It is a 100% fact that everything that we're doing is built off of each other's work. Some people do some really great innovative things, but you've got to stand on the shoulders of giants, as they say, and it just happens every time. But it's encouraging. Anyways, we'll talk about that. But we knew this is probably something we want to look at. I thought we would spend today looking at how you might audit a device like this, and how you might audit and think about looking at the IO control packets that you can send to devices. I'm not entirely sure that that's what I want to look at, and I'm not entirely sure that that's the only path to the driver. I know in my experience, when I've looked at more of a traditional service to driver or management app that talks to a driver, it goes it opens a device and it sends IOCTLs. Someone did tell me that there's a direct draw equivalent, and I'm not sure if that's some kind of Win32K escape or something else. So there's plenty of attack surface here, but I just want to focus on the more straightforward IOCTL type of auditing. So to get started, let's actually I'll explain just a little bit about the two functions you can kind of look at for the IOCTLs and this type of communication. The first one that we actually just want to look at, we looked at last time, but it's back in this Win object EX64. You have your device, and you have some information about it, and then some security parameters. So off the top of my head, it looks like you can access this from low privilege. Unfortunately, I didn't have the time to write code to open the device and send some of these things, and that's because I don't think I'm going to really pursue this much more after this. But there's a lot of tools out there that will do this type of testing. There's fuzzers out there that you can do something similar, but to get at this device is pretty simple. It's just create file like you would any file, and you send it some specific stuff that we'll look at. So bringing that up, the first thing that the user side will call in order to interact with the driver is called device IO control. I do a lot of mining on MSDN. They have pretty good documentation. They also have a lot of good code that, and a lot of times you can just look at this and get a sense of what the developer originally wanted to do. You can also, copy and paste some of this and it'll compile, usually, sometimes not. But I thought this would be the best way that we could look at how someone goes about opening a device, and for vulnerability research purposes, how we might look at the code path on the user side, and we'll follow that into the driver statically just to kind of connect the dots for you. If you like to build fuzzers, this is a 100% good exercise. Build a IOCTL fuzzer. It is not hard. I'll show you how to get all the information, and other people have done it, but if you've never done it before, do it. It's easy, it's fun. I've found bugs that way. It's worth a shot. It's a good thing to look at. So pretty basic. That's all it is. Actually, the main function is not related. It looks like it's mostly just some housekeeping, and they're opening a drive, so they're going to look at some of this statistics off the device, and not really that interesting. But this get drive geometry is going to simulate how every driver interface I've written has looked like this, and that's, we create a file. Their path is a physical drive path, but this could also be this one might be old, it says drive, but either way, you use a similar approach to open up your NV admin device. And the important part is just this right here. So you call device IO control. I think it's an NT DLL, and you send it the IOCTL that we'll talk about a little bit more. That's probably the most important thing in this. And then you've got two buffers. You've got a input buffer and an output buffer, and then a few different kind of flags and other stuff that you can dig into as you want. The way that bugs appear in these, usually in my experience, is a few things. You have access to an IOCTL that should be privileged, and you can call that with a buffer, and think of the buffers as just bytes for right now. They're just a buffer of bytes. Each IOCTL is responsible for the actual structure of that that you can reverse out, but at the end of the day, these are like calling functions in a driver. So I've found some IOCTLs that allow you to create processes. I've found IOCTLs that allow you to write to the registry, to drop files, and they just take in the input buffer, they just take paths, and they do that without any type of access control. Those have gone away, I think, a little bit, since we've been kind of banging on this for a while. I'd say the next level is that you'll have a structure in your input buffer, and they misinterpret something inside of that. Maybe there's a pool overflow, or use after free or something. And then you kind of get into the more esoteric ones, but are certainly related, and those may be like address canonical issues where they may think they're checking that a pointer passed in is a user pointer, and they do some math after they've checked that, and the math actually works out to point into the kernel or something, and so they may operate on data that they weren't intending. A little backstory, I think I think, you know, it's always the pointer arithmetic or math or allocations that seem to trip people up. And it's no different in the kernel. So kernel developers are not immune. They do have a lot more tools, but certainly the same approach to bug hunting that you know, you would apply on a small target should apply to a lot of different drivers. So this IOCTL is just a constant, and there are some that are already defined, and then if you implement a new driver or a new device, you create your own. And I think there's actually, I think there's actually like an IOCTL create tool that Microsoft provides. Anyways, it just makes a IOCTL for you. So here's more information. There is a these are I think these are just the platform specific ones from Microsoft. There's a little bit of a structure to them. Actually, this is, you can read through this. There's a lot to it, but at the end of the day, these constants are what is important, and these constants are what you pass in to your driver. So as we can see, when you call device IO control, you have a DWIO control code. Control code is the specific operation. Think of it as a function. It's just like a kind of a hash for a function, and our buffers. You feel free to get in and read more about this. It's been a while since I've actually looked at this kind of stuff, but there's usually very, very good documentation from Microsoft side that you can use to look into it further. So the first thing you'd want to do, so we know that there's some piece of userland code that is calling device IO control. There's likely in our driver a big map of IO control constants to functions, and then that function will get past a pointer and some other information in an IRP buffer with pointers to your in buffer and out buffer, and then there's just processing on all that. So it differs. We'll look at that part, but it's a great area to look at for drivers especially. So as I was poking around after the last episode, I went and just did a Google search for NVAdmin device, and our good friends and colleagues at Project Zero have been here before. It is not my first time to overlap with Project Zero, but they are, you know, obviously fantastic researchers. They put a lot of effort into these blog posts, and they give out all this information. So this is a good find. I don't get discouraged by this. I think some people, when they're doing target selection, they see this and they run away. My first instinct isn't necessarily to look at this and run away. It's to just kind of see how far they got, what they learned, and if I think I can take it a step further down this path, I'll still pursue it. So what I mean by that is, if they just looked at, let's say there's 20 IOCTLs that are in this driver. If they looked at 10 and they found a bunch of bugs and decided that they you know, that was good, there still could be bugs left. You know, nobody really shakes out all the bugs in the first pass. In fact, if you look at some kind of classic remote Windows bugs, you can see several years before where somebody might have found something similar. So it's not a discouraging thing. It's actually really, really fun. And they do a lot of the work and share it. And that's, again, back to kind of learning from each other and building off of other researchers. They've, you know, give us the straight dope on how some of this works. So I won't read all this. Look, you can see they discovered 16 vulnerabilities. So my intuition about this as a target, I think, has been validated. Luckily, there's more attack surface than just the IOCTL interfaces. And we'll look at their little graph here. I'll post this. Actually, I already did post this in the Discord channel, but one thing I do like is these type of diagrams. So this is validating some of the things we saw last time. We saw this OpenGL installable client driver. We thought there's the Direct3D runtime, and they don't show the NVIDIA driver. They actually show the DirectX graphics kernel subsystem in Win32K. This display mini port driver is likely the NVIDIA driver that we were looking at. So what this tells me is it's complex, which is good for us as bug hunters. There's a lot of attack surface, and we can likely go from unprivileged to at least bare minimum privilege escalation. Let me show you what was exciting, and one of the things that I'm excited about this project for. I said this in the last episode, but they talk about a large attack surface, they talk about elevation of privileges, and sandbox escapes. And so that's kind of was my intuition as well, that the more that we direct connect these IO devices, the more access we'll have outside of we'll have more access to this type of hardware and this type of attack surface in sandboxes, in isolated hypervisor isolated processes, and in cloud type infrastructure. I'm not really sure. I think this is what the info someone else gave me and I read was like the DirectX kernel stuff. I'm not interested in, I'm not knowledgeable on, but I'm interested in. And it seems to work very similar to IOCTLs. What do they say? Essentially IOCTLs. So they have 400 different of these IOCTL-like escapes. And they actually do some nice reversing here, show you the structures. This is all great information. Something more about DirectX. Like I really want to learn more about that. Let's see. Maybe with DDI escape or DXGK escape, you open. Oh, no, this is just what we're talking about already. I thought maybe there was a different interface. But this is really good information that admin device actually calls into DXGK DDI escape. All right, good info. Most bugs were manually reversed and analyzed, some fuzzing, that's good. Never stick to one. It's not fun. It's sometimes you get burned out reversing and manually auditing, and you just write a fuzzer. Sometimes you're fuzzing and you want to actually dig into something and you start doing some manual reversing. That's usually how the best bugs are found. I'll say one thing. If you want your how do I put this? If you want your bugs to live a long time, fuzzing is not necessarily the best route. Fuzzing usually is more commoditized, so a lot of people will write fuzzers. A lot of the fuzzers are the same, and what the code path that they hit inside of software is likely not going to be very secret or very untapped or uninvestigated. And so in my experience, and this doesn't always hold true, a fuzzer is going to find bugs, but they're not going to last a long time. Whereas some of the manually reversed bugs that I've found, and we've seen in public disclosures and stuff like that, have been around for 15 years. So those are always really fun and rewarding. But when you're disclosing them and stuff, then fuzzers are great. So what else? What else can we glean from? Who is this? Oliver Chang. He's doing some good work here. We're learning that userland can get it. A lot of attack surface. Virtual memory, we talked about that last time. That's interesting. Anyways, I won't just sit here and read a blog to you, but this is a fantastic follow-up to last week where we were starting to do target selection. I'm trying to just look through here for additional tips that may be interesting to you. Is this serious? So is this just arbitrary command execution as long as you pass a UNC path? No, this is actually an overflow. Okay. Anyways, a lot of good bugs. Validation. NVIDIA's response. What was their response? Let's see. Pretty good. 3 months for 14. You can, what's great about Project Zero is after the patches come out, they de-restrict the issues. And a lot of times the issues have exploit code in them, or at least a proof of concept code. So if you ever see some of their bugs, go to their, I forgot what issue tracker they use maybe, but go there and look in that and you'll see some proof of concept code. Okay. Again, the essence of ZeroToZeroDay is that I'm going to do a lot of talking out loud as I learn with y'all. So there was one thing I wanted to say, and that was that I think this was accessible from the Chrome sandbox, which is very powerful. So there you go. We've seen stuff. This actually wasn't exactly what I thought, but it's same but different. So they're not using device IO control. They're using these DX GK DDI escape. All right, store that in our head. 14 bugs found there. That's good. So let's think. I'm not going to do this. I thought this was going to line up better, but I'll keep going on with like the more the way that I've used this with device IO control, and we'll see how to look at this in IDA now. So there's when you create a device, there's a big structure, and you fill out function pointers for your structure, and it's basically kind of a handler for anything that you do with that device or driver. So if you open a file, the driver can define, if you open that device, the driver can define a function to handle that open. If you read, it can define that, all the way down to define if it's sent these complete or IO controls. The way that I've done it in the past is going through driver main and looking at where they put the major functions. Let's just look at it. It's been a long time, so I don't know if this driver entry is going to be a good candidate for this because it's so large. But it should be in create device, I think. Let's see. Anytime you see these big structures, we did this last time. Anytime you see these big function pointers, it's likely related. Could be something else, but it's likely related. I'm going to look for create device, but it might be wrapped in a function. So if I just don't find it with scrolling, then I'll probably just look for create device. I think that's what it's called. Driver device, driver Let's just look at create. It's probably been 8 years since I've looked at if you want to search in a window in IDA, it's Alt-T. So if you want to search for strings, it's Alt-T, and it's Control-T to keep going. I think it might be IO create device. We'll see. No, you know what? This returns a handle, and then I forget what you do, but I'd have to look it up. Unless somebody on Discord wants to chime in. So it's on the tip. It's in my brain somewhere. It might be in driver create device, driver entry. Let's do driver in. No, let's do MSDN major. I actually think I know the offset is plus 78 or 74. Major driver, something like this. That's a driver object. So the major function codes are just what I mentioned. They're like system internal codes. So you've got like major create, and this is, I think, when you do like a create file. Let's look. Oh, I know it's here somewhere. So this is a list of some of them. Maybe it's the minors. I don't want to bore y'all with reading MSDN for another 30 minutes, but I'll show you a different way to get to it. Oh, it's on the tip of my tongue. Here it is. So it's in the driver object, add device, and driver entry and add device. Okay. Sorry, sometimes when I read, I highlight. I don't know if anybody else does that, but sometimes when I read, I highlight what I'm reading. Maybe it's a nervous tick. I don't know. All right, so it's a pointer in this. It's a pointer in this driver object, and you create the driver object in your driver entry, and you fill that structure out, and that's basically what the kernel is going to use to dispatch your IO octals that are coming in on that handle. Oh, that's why I don't remember. Okay. Yeah. So it's passed in to your driver entry. Anyways, it's easy to, you forget. I forget stuff all the time. Everybody forgets stuff. It's an easy kind of search to build back that muscle memory on where some of this stuff is. But let's look at a different way. So anytime that you have a IO request come in, you have to it's like a chain. So you have to tell, because in the stack of the kernel for your drivers for different types of things, there's multiple drivers listening. So there's a stack. There's a an order that they call altitude, I think is the right terminology. And so if you're the first driver and you don't know how to handle an IOCTL that comes in, then you need to pass it down. So you need to pass it down, and Windows will pass it down to the next listener, or if there's no listener, it'll kind of complete the request. So there's a function that it does that with. Sorry. All right, typing's hard. And it's IOF complete. I think I'm right. IOF complete request. Yeah, so it's a macro. I'm not sure if the compiler actually does something different, but we can see from IO complete, from this macro, that indicates that the caller has completed all processing and is returning the interrupt request packet or IO request packet, I forget which one it is, back to it's done its thing and it's done with it. Otherwise, it'll pass it down a thing. Yeah. So we're going to go backwards. We're going to look for functions that call complete request, because what that tells us is that implementation or that code there is done with a request and done with an IO request. So you can really quickly go in and kind of start reversing out what some of these IOCTL handlers look like. This is pretty standard. This may not be exactly for our IO request, but we always will see this select type branching. And the reason is because if you think about these different packets, they'll come in and this driver may handle 30 of them. So it's going to do some type of byte comparison or maybe a D-word comparison and dispatch it to the right subroutine or right routine. And so I bet, let's just poke around a little bit and see if we actually can see this a little bit better. I'll say one thing, the IRP, I still struggle with the IRPs inside of IDA. This is an IO request packet, yeah, not an interrupt request packet, IO request packet, and it is very Windowsy. So it's very structures within structures, linked lists. I think there's some in here, but inside of IDA, things like this get a little bit hard to make look nice in IDA. So I still struggle with it. I'll show you maybe in a later episode where you can create structures inside of IDA, and it helps a lot. But for some of the IRP stuff, I've never been able to really get a good technique down for enumerating each field inside an IRP. So if we go back and look at IDA, IDA knows, because we call this IO complete, that this first argument is an IRP. We can see that in RCX, which will be the first argument for Windows 64-bit. And this is kind of what I mean right here. This has a structure offset, and I know that it's an IRP. So let me look and see if, let me add, let's just try it. We'll see what happens. We'll do it live, as they say. If you go into the structures window in IDA, and I forgot who turned me on to structures, but I am obsessed with making structures, because once you do it, it's kind of a pain, but once you add structures and you start to define your types and your sizes, and you start to reverse and figure out what certain things are, IDA becomes really readable, because you could start to go from RCX plus 30 to RCX plus IOCTL code. and that makes it really readable. And then if you're a hex rays fan, it makes hex rays a lot more readable as well. I don't use the decompiler much. It's very expensive, and there's some really good decompilers that are out there that aren't integrated, but it's worth it a lot of times, I guess, especially if you're reversing malware, probably, or reversing something that's just obfuscated, or maybe encryption, or I don't know, something like that. But for standard code, I haven't really needed it much. So we'll add one. We're going to add the IRP. I'm just looking to see if it's already in here. IDA, I think the way that this works is IDA will just kind of enumerate the parameters to some of them, and go ahead and add these for you. So let's add a new one. If you don't have insert on your keyboard, insert or break, then it's always fumbling around to try to remember how to create some of this stuff. But luckily, I have my keyboard connected. So let's look for IRP. There's an IRP. I think that's the one, but there's our device object too. If we wanted to look at that one, yeah, we're good. This one's it. So I'm going to add this. I'm also going to add that device object if it's not already added. So I'm doing this by going down to the bottom and hitting insert, and then clicking add standard structure. You know, it's got some parameters that I don't know if I've ever used. I might have used the union one, but I haven't used the other one. So let's look at our driver object or device object. Was it driver object? There's two of them. And then you can plus shift alt plus. Where's my plus? I don't have a numpad on here. Son of a bitch. This is where I always forget. I don't have the 10 key or whatever, so I have to go to right click, unhide. I don't remember what the hotkey to do that is, but we can see in our driver object that it's got these defined. Why did IDA change the coloring on their structures? No. If I want to do, I'll show you how to do a new one. Let's say my struct sample. Go to it and you just do like DD and it'll create fields. You go down, DD, create fields. You just do D, 1 byte, word size, D word, Q word. You just keep hitting D. Huh. Actually, it already has some type definitions. I'm not sure. I've never seen it like this. Usually it looks blue, but I haven't used this version of IDA before. Anyways, we can see how our driver object now has fields, as you would expect from a structured type definition or definition. And then let's go to our IRP. God, they have... I don't know what these are. Somebody, if you know, please help us out, because I have not seen... I do not know the difference in all of this. All these different structures with this type of hash behind it. Obviously these are related, but oh, this is a union. Oh, this is a struct. What? Oh, okay. Okay, this is some way that IDA does nested structures, because this is here, let's do this. Now I'm curious. This is you know, if you're not curious, then you're probably not going to be that successful. The downside is curiosity sometimes takes you off track and gets you distracted. But I am interested in this. We'll look at this like this. Hang on. Oh, Windows, come on. MSDN IRP. Pull that structure up again. I just really want to hammer home how useful this will be once we just kind of, once I look at it a little bit. I just feel like I'm on the wrong structure. But I'm just going to interpret it. Where are these APCs? It's associated. So associated is a union. So they've got this, which is the union. Let me clean this up a little bit. Hide, come on, hide all this junk. So the associated IRP is here, and that is a union of a structure. Huh. Yeah, I mean, this is one problem. IDA's confusing me. Why do you confuse me, IDA? It's not IDA's fault, it's my fault. We'll move on. So here's an overlay. I think these are they're just off. Okay, anyways. Back to what I was trying to show y'all is that once you have this structure added, you can then you can go back here and use these constants. So this is what I was kind of getting at, that it gets, for me, it confuses me. I've never spent the time to try to figure out what the right one of these to select is, but you can see how it starts to give you a readable structure field, so you know that this value is being stored inside of this IRP. The offset's 30. I might go look at a header file or something to really run it down, but honestly, I don't care at this point. What else do we have? We have EDI, RCX. This is really the only thing they've been using. So let's go up one. The same IRP packet. Again, this IRP is here, I think. Nope. It was RDX. RCX is also something. Oh, it's just checking if this value that they care about. So they dereferenced the one that we saw. I think it's K. Let me try K. Nope. H. Nope. Nope. I defined a local variable, which is not cool, but it's T. That's what it is. T. And that'll bring you up your IR, the same window. If you right click, I usually right click, but if you like to use only keyboard, then they're here. You can look at what those are. So it grabs that, just make sure the lowest byte has these flags set. Another good one you can do, if you're dealing with flags, then you can hit B. Like if you have some kind of test or and or something like that, then you can hit B and take it from hex to binary. All right, let's keep going up. So we got R14. We had RDX. Our IRP is in RSI. We can see because of this branch hasn't really touched RSI that we these two branches are working on the same IRP. In my head, what I'm doing, I don't want to go through every single call. Because it's too much information. So I'm really trying to identify where it's interpreting all of those IO codes. And we might need to, I might need to look up and refresh my memory where the where that code is actually pulled out of your IRP. But normally in reasonable size drivers, it's pretty straightforward. This is telling me we're probably close. You've seen not only in this graph, but we've seen in others where it pulls out this value and it starts doing a comparison check. This is just a constant, and nothing off the top of my head says that this is some type of magic byte or some type of thing. It very well could be. We could be looking at the actual input to the input buffer, but I don't know. Let's just right click here and see what. So the user IO buffer IO USB. I don't remember how far in the IO packet is. I'd have to look it up, but it very well could be this first value, or that could be the actual value constant. Let me just see. So I'd probably just label this like this. IOCTL handler. This one's just for y'all, maybe. I don't know. Maybe it is. I don't know. We'll find out later with more reversing. I don't plan to do a lot of hardcore reversing. I think it gets redundant, and I don't think anybody wants to sit here and walk through the binary. If you do, maybe in a later one when we get closer to perhaps auditing and wanting to walk through every line of code, I'll certainly do it then. But right now, I'm just trying to save myself time and show y'all some of this other stuff. So this is back to our big driver entry, and right here is our a pointer into R15, which will probably be stored hopefully in our driver function, in our driver object or device object. I'm sure there's people, maybe there's people watching that are probably screaming at me that I'm close or very far off. Let's check Discord. Maybe we've got an assist. Nope. Okay. Anyways, you can follow these paths. This is how I do it. I mean, you eventually get there. The thing to remember about reversing is you're going from nothing in something like this. You're reading as much as you can. You're kind of going back and forth in the code. You do that a lot until you start to piece some of it together using the little bit of information that you have. So it's all about discovering pieces of information, and then once you have enough, putting it together, getting a better understanding, and doing that over and over. We'll look at one more of these cross references to IO complete requests. I said I don't use GraphView very much, but here I am using some GraphView sweetness. Usually when people are doing this, it's in some kind of switch or something. They're subtracting from the same constant. So EAX may come in as whatever this is. This is wrong. This is... Huh. Anyways. So they'll start and they'll subtract it, and usually it just means there's some kind of case that they're looking for. You can see they keep checking constants. So some of these could be related, but if you see stuff like this, it's most certainly kind of switch. And we're reversing through GraphView. All right. Come on. Some mutex. This is cool. I'd have to look that up. It's cool because if you remember from the beginning, I'm not necessarily interested in the local privilege escalations. I want to do something more in these types of interrupt, which will send it straight to hardware, or go through an interrupt handler. May be interesting. This could just be some kind of trap in some kind of fail case, and it wants to actually crash. This could be like bug check, although I know there's a wrapper for throwing a bug check error in blue screening. All right, let's go back. I was hoping I could find a cross reference that would perfectly show what I'm getting at. Let me just work through real quick. If I don't find anything in 5 seconds, not 5 seconds, 1 minute, then I'll keep going. I hope y'all kind of got the idea. Again, do it yourself. You guys are watching and working as I'm working, so there's nothing keeping you from pulling up your own driver or a driver that you like and trying it out. When you have a binary like this that's huge, you have to really learn how to see quickly, how to not get distracted by going down every single little bit. The kernel's a lot easier to do that with because usually it's a lot more structured than user lane code. So we got our handler here. We're back in driver entry. But you can't possibly, oh, wow, look at this one. Okay, this one could be it. If y'all can't see this epic graph over here, then so ideally what I would see is a lot of access to this, but I'd want to see more branches. So this is probably not it, but it could be. This very well could be right here. Wait, who gets R13? So I don't use R13. So this may be the value that we, wait, yeah. Right. So this kind of control mouse wheel zooms in and out. Let me just make this closer. So the only problem is that the font it's not a true type font or something because it gets real ugly. See, it blurs. So they're doing, I don't know how IDA draws their graph, but so this is kind of what I'm getting at, right? Like here is a constant that is not a pointer. It's not referenced. It doesn't look to me, you know, like something you would divide by or a magic number. It very well could be this group of IOCTLs that we want to audit. And we can see that the first thing is compared against 18. We know how to look up your structure offset for your IRP. Where are you? IRP. That's not you. You son of a bitch. Where's that IRP? Here it is. Ah, here we go. Yeah. I think that's the right one. Master IRP. I'm out of practice on that, but I'm pretty sure this is... Nope, that's not it. I'm on the wrong one. Anyways, I feel like I'm getting close. If I spent a little more time, I probably could find these handlers, but this is what it looks like. Okay, so you've got constants, you've got what will be, you know, I just have to spend a little more time getting my structures right. The IOCTL code that's passed in from userland, they're comparing it to something. If it's above, it goes one way. If it's below, it goes another. If it's 0, this could be an abort. It could be something else. Probably exits. So we start to see that it's looking at these constants. You see them pop up, you see them subtracted, and you see branches. And we see that multiple times. We see some subtraction. So it's a constant with multiple options, and they want multiple branches for different values. And that's what the IRP handlers look like. They look like multiple values, depending on the value, branches to the implementation of that. And that implementation is what we actually would want to audit. So the steps that you would take are open your driver, you know, find the cross references to complete or go the driver entry route and enumerate it, and then identify all your constants and try to build a map of your constants and maybe the real values. You need to extract those because that's what you'll pass in to your user side. So your device IO control, the second argument will be this constant. And if you have enumerated all of them, then you can go in and find the handlers or the implementation for them and know that from user land specifying your code, you can hit this. And that's one of the most crucial parts to finding vulnerabilities. Mapping what the user input eventually hits inside the code or how that's handled, and it's almost always going to be some type of evaluation of what the user sent and you know, a subroutine or a function that handles it, or multiple functions, or it's a class or whatever. But identifying that, you can run your fuzzer against it or whatever. So that's a little bit on IOCTLs. I wanted to spend that time today because I'm not super interested in this route. I'm interested in, let's see, real-time code might have a hookup. Yeah, so the question on Discord was, does a constant match a control code format? Yes, they do. They're not always right, I don't think. So there's it's in the DDK or it's in the SDK, but basically there's an executable that Microsoft has that you just pull up, click it, and maybe you do, it's been a long time, maybe you do fill out some of the format of this, but it generates one for you. So this is, you're probably spot on. This is probably what that app uses, and there is a little bit of a format. Usually when you're reversing though, you already know some of this, but it's a great link because maybe what we're seeing up here is an interpretation of some of these bits, but I've never really paid too much attention to the codes. If they're non-standard Windows ones, standard Windows ones are defined and they do follow this format. So we looked at some before. So IRP, MJ, PMP. These are pretty structured, and you can read a lot about them. But for ones that are specific to the vendor that implements the driver, they're not always that structured that I've seen. Okay, so what I was saying is I've done a lot of work on kind of auditing these interfaces. We know that Project Zero was pretty successful. I think for any of y'all listening that want to kind of play along, write a fuzzer, go through this, see if you can just start hammering on it, and it'll be good. It'll be good exercise. This one's a little more complicated than a lot of them that I've seen, but it's still, I think it'll follow the same flow. And try out some fuzzers and whatever. But I want to poke at kind of what we talked about last time, like more of the graphics programming side of things, so shaders, things that will be loaded onto the actual GPU. Not necessarily local privilege escalations, but something that gives us the ability to break out of VMs. So there is a possibility that you can hit some of the driver on the host system from the VM. I think it's probably unlikely, but you never know. So I guess that's all to say. This is a great area, but it's not what I'm going to keep looking at. And those are kind of the reasons. I want to find something that I've never done before and something that is very different. So, I thought it would be a good time to at least show y'all how to do some of that, or at least give you a few pieces of data. What I do want to look at again is just kind of a different approach, and I found a really cool project. So Google actually has Project Zero. Actually, this is great information. I want to kind of look more at the client driver and the maybe not Win32K, since this is all pretty much sandbox now, but definitely the DirectX kernel is super interesting to me. It handles video memory, and so maybe we can do some cool stuff there. This doesn't seem to break out either, but at some point some of our code has to get to the driver, especially if it's going to be optimized for something like compute or machine learning or whatever. So there's this really cool project, and this guy has created a I think he worked for VMware, but this is a VMware SVGA device developer kit, and he's created this library that allows you to directly from VMware interact with the VMware SVGA driver, and I think it looks like probably also the host implementation of that. So however the host is mapping the GPU to the guest, or maybe the guest has direct access to the GPU through the driver. But what's really neat about this is he's created a library to run bare metal graphics code inside of VMware, and it runs on his little kernel that he's written or whatever, and you load this image, and whatever program you develop runs directly in VMware without any operating system. And what I think is really neat about that is it allows us, if we want to, we might be able to create a fuzzer in this that fuzzes from within the VM into the host and see what we can do. It might allow us to map some memory. So it's really great. It's called VMware SVGA Device Developer Kit, and it is on GitHub now. This is the old version, but let me show you the GitHub version. Let's see if I pulled it up. So it's right here. I'll link this in the channel. I'll link both these in the Discord channel. But this is neat. And so I think I'm going to look at this. I may do a little bit more research before next episode. see if this is something that's interesting. Again, I'd love to find a VM breakout, or I would love to find a user land to some kind of code execution actually on the device. But this was a fantastic find. If you go into the bin, he actually has already built VMXs for all this. So that bunny picture we saw, you can look at the pre-built VMX. If you have VMware, download this, run it, you'll see the bunny, and he has his code for it. So here's the bunny code. I don't know what this is, but here's his main.c. So he's creating some textures. He's got a library for this, and then you know, he just writes what basically shaders are written in, and is able to draw it direct in hardware. So from a fuzzing perspective, this could be incredibly powerful. But anyways, this is what I'm more excited about. However, go check out IOCTLs. Go read the Google page. You know, search for things. There's a lot of research that's been done on this. You'll learn way more than I'll show you, but hopefully in this kind of episode, we've done something a little different. But we're still in target selection. I'm going towards this on the right-hand side. We might do another episode of target selection. I may just decide to dive in and spare y'all, but I really honestly believe target selection is part of the art of VR. A good target is rewarding and fun, and your curiosity can help push you through the monotony of reversing sometimes. And then, you know, also if it is brand new, then you have something to share with people and get others involved in looking at it. So that's kind of what I want to do with this. But that, you know, it's going to take time. So anyways, I'll sign off now. I hope you enjoyed episode 2. Give me feedback. Let me know if audio is good, and I'll find a place to upload these recordings. But anyways, have a good night, morning, wherever you are, and thanks for watching, and thanks for the support, everybody. I hope this is fun. So see ya. Take care, everybody. Bye.